Good day, class. You are welcome once again to the GST 118 class. In our last class, we discussed man and his cosmic environment. In that class, we had the definition of the key terms of a lecture. We defined what cosmic is with the man. Then we discussed the environment. We tried to define what the environment of man is. In that environment, the environment we said was further divided into two: the cosmic environment and the terrestrial environment. It's suffice to say that in that class we agreed that the terrestrial environment is an integral part of the cosmic environment. But for that particular class, our interest was the cosmic environment, which is the universal environment where man finds himself. In order to understand the cosmic environment and how it relates to man, we further discussed that was what gave birth to astronomy. And we briefly mentioned the different aspects of astronomy. We discussed the solar system. We discussed the hypothesis about the origin of the solar system. We discussed the different planets in our own galaxy. We further discussed Earth as the only planet where man thrives and lives. We discussed the characteristics, we discussed the size of the Earth, we discussed the spheres of the Earth. Then we discussed the characteristics of the solar system. We discussed, among other things, the spheres of the Earth, which are the atmosphere, the lithosphere, the hydrosphere, the biosphere, and the lithosphere. We further said the atmosphere consists of three subspheres, namely the troposphere, stratosphere, ionosphere, which is further divided into mesosphere and thermosphere. We'll be moving on from that today to discuss the scientific method, which is the next chapter and the next topic in the syllabus for this course. We'll be looking at what is science, what is methodology, what are the various branches of science. We'll be looking at the history of scientific method, the contributions of the Greeks, the contribution of the Arabs. If time permits, we'll look at the steps involved in scientific method, and we'll look at the steps to be taken by a researcher when performing an experiment or a research. What is science? The best way to really explain what science is to know what is not science. Science is not explanative, doesn't give itself to discussion, unnecessary discussion. Rather, it comprises of experimentation, observation. So if you are to define what science is, I would say science is a study of physical and natural world through observation and experimentation. It is also the systematic study of the structure and behavior or the phenomena of phenomenons always seen around us through experiments and observation. There are different branches of science. We have physics. The study of physics focuses majorly on laws and properties that governs the behavior of matter. It often involves things we can't see or touch but can prove through experiments. At least we can prove gravity. We know that if you jump up as a human being, definitely you are coming down. Physicists study energy, study mechanics, study motion. Physicists study waves, electricity, nuclear reactions, among others. One other branch of science is chemistry. Chemistry is the study of the chemical composition and reaction properties. It studies the properties of matter. Chemistry involves how atoms, the smallest particle of the world, binds together to create compounds, among other things. Then we have biology. Biology is the study of life, and the principles and compounds in chemistry forms the foundation for it. Biology spans from studying the most minuscule structures inside cells called organelles to giant masses of land with specific climates called biomes. Biology studies cells, genetics, anatomy, physiology. You can just think of it. Then we have earth science, which is the study of natural processes that shapes the earth, such as geography, oceanography, meteorology, and such likes. Then what is methodology? It is a study of methods. Initially I said science is majorly the study of the physical and natural world through observation and experiment. How do we carry out this experimentation? Methodology is one study that looks into what are the different methods through which scientific experiments can be carried out. That is, when we now look at scientific methodology, it's telling us about the methods that we use for scientific experiment, that we use for scientific problem. Science, one other thing about science is it acquired its originality by detaching itself from fables. Whatsoever you will say in science, we want to be able to prove it. We want to be able to say, okay, based from experiments, based on what we've done, based on what we've observed, based on what we've gathered through observation and experimentation, this is the fact. Science deals with what has been tested and known to be factual. We'll briefly look at the history of scientific method. I said there are different methods of going through this. Then what brought about scientific method? How do we come? What is even the beginning of scientific method? Under this, we'll be looking at the contribution of Greek philosopher. So we'll be looking at the influence of Muslim on the history of a scientific method. Then we'll look at other scientists, and we'll look other scientists that contributed in one way or the other to the scientific method. Then we'll look at where is the scientific method in our current dispensation. Then we'll look at steps involved in scientific method. What is history? History of philosophy of scientific method. One thing that is peculiar is that it will not be far-fetched for us to say the history of scientific method starts from Greece and ancient Persia, because they were seeking on how to dominate each other while they were fighting wars. While later, about scientists in Babylon, India, Egyptian astronomer physicians also developed some empirical ideas. The Greeks were in fact the first to develop what we recognize today as scientific method. Initially, ancient Greek philosophers did not believe in empirism and saw measurements such as geometry as the domain of craftsmen and artisans. Philosophers such as Plato believed that all knowledge could be obtained through pure reasoning, and there was no need to actually go out and measure anything. And that is contrary to what science believes. We want to take measurements, we want to look at it, we want to be sure that this thing really is. It's not purely because we reason it to be that it should be. We want to know exactly what subsists. Aristotle, an ancient Greek philosopher, can be regarded as the father of science, and he was the first to realize the importance of empirical measurements, believing that knowledge could only be gained by building upon what is already known. That is, you move from a known region to an unknown region. Measurement and observation, the foundation upon which science is built, were Aristotle's major contribution. He knows his contribution is majorly on measurement. When you observe, you measure. When you observe, you write it down. When you observe, you take recordings. The contribution, he proposed the idea of induction as a tool for gaining knowledge and understood that abstract thought and reasoning must be supported by real-world findings. The fact that you reason out something, then you must be able to substantiate it using an example that is common, that people can relate to it. There are three major steps in his contribution to the scientific method. He said, number one, study what others have written about the subject. If you have a thought about a subject matter, you study what people, researchers ahead of you, have said about such. What are people around you saying? What the authority on this in this field is saying? Then you look for general consensus about the subject. What is the acceptable opinion? What is everybody saying? That is what Aristotle meant by general consensus. What is the agreed fact about this particular subject matter? Then you now perform a systematic study of everything, even that is related to the subject matter, even if it's just partially related. Once it has anything to do with the subject matter, then you look at it. This is the first scientific method that has, with literature review, consensus and measurement. In about 200 BC, the famous library at Alexandria saw the first introduction of library cataloging, essential for any scholar conducting a peer review. From this, I want you to note that Aristotle, who is regarded as the father of science, is the first to postulate this scientific method based on empirical measurements and observation. Then, when you're listing out what it says, so once again, study what others have written about the subject, look for the general consensus about the subject, and then perform a systematic study of your own. After you've looked at what others are saying, you've looked at what others have written, you've looked at the contributions of others, then you will now perform your own, ensuring that you touch everything that relates to the matter at hand. This brings us to the contribution of Muslim towards in the history of scientific method. The early Islamic ages were a golden age for knowledge, and the history of scientific method must pay a great deal of respect to some of the brilliant Muslim philosophers of Baghdad and Al-Andalus. They preserved the knowledge of the ancient Greeks, including Aristotle, but they also added to it. That's one special thing about research. You build on the work of others. Ibn al-Haytham was one of the known Muslim scholars that worked on history of science, that worked on scientific method. He developed a scientific method that was very similar to what we now use nowadays. He said, state an explicit problem, that is, recognize a problem based on observation and experimentation, that is, based on what you observe. Okay, this is going on. How do I go by it? That's stating the problem. You've observed the problem. Then, does it really exist around? Then you experiment about it. Then you raise an hypothesis, which is an intelligent guess on what you think should be the answer. Then you test or criticize this your assumed guess through experimentation. Now interpret the data and come to a conclusion, ideally using mathematics, and you publish the findings. Ibn al-Haytham brilliantly understood that in order to get a good outcome, then you need a controlled and systematic experimentation. you need correct measurements, and thus, in order for you to discover new knowledge and build upon existing knowledge, systematic experimentation and measurements are essential. Other contributors to the scientific method include Al-Rawi. Those are Islamic contributors. He was the first scholar to use a recognizable peer review process. We have Abu Jabir, known as Jabbar, an Islamic scientist often referred to as the father of chemistry. He was the first scholar to introduce controlled experiments and dragged alchemy away from the world of superstition into one of empirical measurement. Then we have Ibn Sina, one of the titans in the history of science. He proposed that there were two ways of arriving at first principles of science: through induction and experimentation. Only through this method could the first principles needed for deduction be discovered. These contributions to scientific method and to the tools required to follow them made this into an Islamic golden age of science. However, with the decline of Islamic houses of knowledge, the history of scientific method passed into Europe and the Renaissance. When we talk about the Renaissance, we talk about the reawakening. Then this some of the European scholars that took the knowledge of the Greek and the Islamic scholars' knowledge to then they built on it. We have Roger Bacon, we have Francis Bacon, we have Descartes, we have Galileo, we have Isaac Newton. The scientific revolution reached its zenith with Isaac Newton. Virtually almost all of you in this class have heard one thing or the other about Isaac Newton. If I should ask you, have you heard about Galileo? You find it difficult to tell me, not to talk of Abu Jabir or Ibn Sina, not to talk of Aristotle. Okay, Aristotle's name is also common, but probably you may not even have thought about him being the father of sciences. Now we look at the history of scientific method and the 20th century. That is the wake of the 20th century up to the 21st century where we are in. We have, as the scientific method became developed, especially from Isaac Newton, they became these developments became the new drive for scientific discovery in the new centuries. However, the ideas were based in many scientific were based at a time where most scientists were polymaths working in many scientific fields. You know, all those listed above, you could see them being experts in this field, being experts in another field. Some of them were into philosophy, some of them were into theology, some of them were into reasoning, just logic and reasoning. Just think about it. They had their feet in so many things at the same time. They were really not purely scientists. Science gradually began to move away from those areas and developed into a separate area of study. In addition, the increasing complexity of science and the increase in both breadth and depth made it impossible for a scholar to work across disciplines. As the time goes on, this new dispensation where we are in, you now have to specialize in one field because the knowledge has been broadened. You can no longer combine physics with chemistry, with biology, with religious studies. You have to be specific. You have to identify a role that you want to work on. You have to be sure that this is what I want to do. Then you insert yourself. Then science, that is science, now split into different aspects. We now have chemistry. You have those who specialize in physics. We have those who specialize in biology. And one funny thing is, even for this split, we have these branches also splits downward. You see those who now specialize in biochemistry, those who specialize in nanochemistry, those who specialize in cell biology. You could I think you can get what I'm trying to say. As a result, the 20th century saw a huge change in the scientific method as philosophers of science attempted to address this. Probably the most famous of this was Karl Popper, who understood the limitations of the old scientific ways. Popper's main point of attack was establishing that science was not infallible. Well established scientific discipline often followed the wrong path and generated incorrect theories. This led him to question the very definition of science itself, and so he tried to develop a scientific method that addressed the limitations. Previously, the definition between science and non-science revolved around empirical techniques and inductive method. Another contributor in this era was Thomas Kuhn. He built his idea around the idea that science developed conflicting theories about how everything worked. Experimentation would lead to one of these theories becoming dominant and accepted by the scientific community. Kuhn christened this a scientific paradigm. That brings me to, what are the basic steps of scientific method? The scientific method is a process for experimentation that is used to explore, to observe, and answer questions. We want to talk about asking questions and preferring answers to this question. Not all scientists follows one rigid steps. The steps, the methods involved in scientific experimentation is as many as the number of scientists we have. But one major thing, no matter how modified the steps may be, the goal remains to discover the cause and effects relationship by asking questions, gathering and examining evidences, and seeing if all the available information can be combined into a logical answer. But one thing is, no matter when the process of experimentation starts, new information may spring up that may force you to go back a step or to repeat a step. In this case, it is called iterative process. Whether you are doing a science project, a classroom science activity, independent research, or any other hands-on science inquiry, understanding these few steps that I will be explaining briefly will help you focus on your scientific question and walk through your observation and data to answer the question as well as possible. You may not get the answer you wish, but at least to the inquisitive mind you have, you'll be able to provide an answer to a reasonable level. What are these steps? The first step is make an observation. If you've followed me from the beginning of this class, you would have observed that I kept repeating the issue of observation and experimentation, which is the bedrock of science. Make an observation. What do you see? What do you want to solve? What's the problem? What's the phenomenon that you see that you want to look into? Then you ask question. What have you observed? What is really happening? Okay, why is the wind coming from this direction? Or why is the rainfall here going this way? Why is the weather different? That's an observation. Why are there more boys in my class than there are girls? That's an observation. Okay, probably let me say I observed that there are more boys in this class than we have girls. I've made an observation. Then the next thing is to ask a question. Why? Why do I have boys in this class more than I have girls? That's asking a question. The next step I would have to do is to do background research. Why? In order to answer the question why, I may have to look back. I may have to look at the whole level result, the choice of subjects, what each candidate would love to do. Why? Okay, probably most of them are in science related courses. They don't really need to take this. I'll make a wide study as a background research. I start from the scratch. I put together a plan for answering my question. which is why are boys more in this why are boys in this class more than the girls I have. Then I may want to visit the library if necessary. Then if it's a scientific problem, probably looking at ways to get more edible salt, a healthy salt that will, I don't know if you understand. Let me look at how to go through it, or providing a drinkable water source for all students in Ekiti State University. I will want to look at what had been done as regards to this. Why is there no potable water, or enough potable water in the system? Is there a way to, what are the steps that have been taken earlier? How can I improve on the steps that have been taken earlier? Those are those are things that I want to look at during my background research. Would I need to visit authorities to ask questions? Would I need to visit the works department? Would I need to visit the geophysics department? Do you understand? You look at things like that. Those are things you do during your background research. When majorly your background research is done to find information, you do look at research papers, and if it is an academic experimentation, you look at research papers, things that others have done, what others researchers have done prior to your own study. Where were they? What did they see? What did they get? Is the observation the same as my own observation? What they learnt, what they find, is it relevant to what I'm seeing? Is there any difference? Then I look at this, I look at bibliography and the likes. Then based on what I've seen in the background study, I construct an hypothesis. I said an hypothesis is an informed guess. It is a possible answer to the question I raised earlier. I said ask a question. So my hypothesis could be a possible answer to the question I raised. Although in order to test my hypothesis, it may require a great deal of background research and inquiry. The purpose of my hypothesis is not to arrive at a perfect answer. It does not really mean that because I've given an hypothesis, it must be the perfect answer. A good hypothesis allows me to make prediction. One thing about hypothesis is it should give me opportunity to test my options. It should give me an opportunity to look into areas that I may not even have considered before. Then you test. The next thing is to test your hypothesis. One thing, when I'm constructing an hypothesis, when I'm deciding to state my hypothesis, it must be testable. It must be verifiable. I just don't give an hypothesis that cannot be tested. This is done by, and how do I test my hypothesis? It is done by doing experiments. I look at, in order to accept such hypothesis as a scientific theory, I must be able to experiment what I say, what I've stated as an hypothesis. It must test a single variable by keeping all other variables in control. In order for my hypothesis to be accepted as a theory, and the experiment in order to prove this hypothesis must be controlled. That is, it must test a single variable by keeping all other variables under control. The experiment must also be reproducible so that it can be tested for errors. If I'm testing my hypothesis, the experiment that I do, the experiment that I perform must be doable, must be experimentable at any given location. That the experiment was carried out in Ado-Ekiti should not preclude or should not make it impossible for another researcher probably in the US, from carrying out the same research and arriving at the same answer. My experiment must be reproducible so that if there are errors in my own, others can point it out. And at the same time, if there are errors, if I should repeat the experiment, I should be able to note out the error. Then after the experiment, you analyze your data and draw conclusion. As once the experiment is conducted, the next thing is to analyze the data you collected from the experiment. You look at it, then you go back to hypothesis. Does your results, the data you collected, does it align with the hypothesis raised? If not, then you draw your conclusion. And the last step is to communicate your results. Once again, I run over the steps involved. You ask a question, you do background research, construct an hypothesis, then you test with an experiment. Is the procedure working? If no, probably when you start the experiment, you see that what you set up is not working. Then you go back, you troubleshoot, you check carefully all the steps and the setup. Then you test again with an experiment. If it's not working, you analyze your data and draw conclusion. Initially I said there may be new information around that makes you to go back a steps, iteration. When you have new information at hand, you go back, you test again. Then if it still works, you analyze your data and draw conclusion. If your result aligns with the hypothesis, you communicate it. If it does not align, you communicate your results. At the same time, the data you collected becomes other set of data for future projects, for future researches. That is, research never stops. Science doesn't stop. It's a cyclical process. It goes on and on. Once a problem is being solved, another problem is generated. There was a time there was no electricity. There was a time there were no fossil fuel. Now we have fossil fuel. There was a time there were no cars. There are cars now running on fossil fuel, and we are back at the point where we are now saying we want a greener environment. We want an environment where the ozone layer is not depleted. Science is continuous. Research is continuous. As you improve on it, the problem will always arise that needs solution. Then, as a good scientist, what are the steps and procedures for conducting scientific research? Based on our previous discussion on scientific method, now we want to conduct a scientific research. What are the process? What are the steps you need to take? 1. Define your problem. What the first step of the scientific research process entails is defining the problem and conducting research. For any research work, for any scientific research, the first thing is define your problem and conduct the research. 1. How do you define your problem? Select a topic of interest. What is your area of interest? Look into literatures, read scholarly articles. That is what we call the literature review. Look at what other scientists have done. Look at how far they've gone. Then your literature review helps you to understand what others have done as regards to your topic of interest. Peradventure, I was saying something like looking for a free and clean environment, an environment that is free of toxic waste. What have others done as regards to this? After picking my topic of interest, I look at what others have done within my locality and outside my locality. If those outside my locality have gone further than we have gone in my locality, is one thing for me to look at what they've done, then I bring it out to my locality. That may be what I need to do in my own area in order to attain a cleaner environment. Select a topic, read scholarly articles, read widely. Don't limit yourself to what you have in your system. Look around, look out, look inward, look outward. There are so many ways in order to get your articles. You have primary sources of information, we have secondary sources. You look at what others have done. Basically, when you do literature review, then you look at the gap you want to fill. What are the gaps you have seen? Probably the topic of your topic of interest is what someone has worked on. You look at where you can come in, you look at the lapses, you look at what you believe if this person has done would have given a different result. Then you, after doing that, you narrow down the broad topic into specific research question. Based on your literature review, you can now draw out research questions that you wish to answer. Then after this, you formulate hypothesis. I said earlier that an hypothesis is an informed guess. Your hypothesis must be concise, it must be testable, it must be falsifiable. Then it must define variables to be researched into. You just don't make a vague statement. You make statements that are concise, you make statements that you can test, you make the statement that can either be true or false. Then you make statements that are related to your variables of interest, that are related to the topic at hand. You just don't form an hypothesis of and or anyhow. Then the next step is to design your experiment. How do you plan to collect your data? How do you plan to what are the data that you need for this experiment? What is your population? Where do you want to source your sample from? How will you obtain your sample? What answers the question where is your population? Then how do you go about your sampling technique? How do you obtain this sample? That is what we refer to about sampling technique. You know your population, you know the sample you want to take, you know the sample you want to deal with. Then how do you get this sample? Then the next step is determine the control and other measures you need to carry out the research. I said earlier that scientific research gives you better results when it is controlled. Then you have to schedule the time and date for the experiment. Then the next step is to collect data. One thing I want to point out here is you must record your data prior to the experiment. Data you collect prior to the experiment, that's the pre-test information, you note it down, you record it. Then you conduct the experiment where necessary. After conducting the experiment, record the data you obtain from the experiment. Then that brings, after you now have to set up data. The next thing is data analysis. There are two major types of analysis. We have descriptive analysis and we have inferential analysis. Descriptive analysis makes use of descriptive statistics, while inferential analysis makes use of inferential statistics. Descriptive analysis is done when you are only presenting the result as you see it. You are presenting the information, the data gathered as you see it. You are not manipulating it. What you are presenting is not based on manipulation. And the descriptive statistic tools used for this include mean, standard deviation, you have pictorial reports. Those are descriptive. You just want to describe the data you've obtained. It describes. Descriptive statistics describes. It doesn't manipulate. You can't draw any inference from descriptive statistics. So when you analyze your data descriptively, you are describing your data. For example, if I want to describe this class, the GST 118 class consists of 3 groups of students. I can do a pictorial view of the group of students I have. We have those in the engineering, we have those in actuarial science, we have those in the religious studies department. Those are descriptive statistics. I can present it as a table, I can just present it as a bar chart, I can use pictogram, I can use pie chart to describe the scenario of my class. I'm not manipulating, I'm just describing what I have. But when I now have to draw inference on why there are more boys and girls in this class, probably I want to draw inference on your performances, then have to use inferential statistics, because I would want to draw inference from your performance in order to know if indeed boys and girls performs better. Then what are the inferential statistics that you could use? You could use t-test, ANOVA, ANCOVA, and so on and so forth. Then the other step is conclusion. After analyzing your data as a scientific researcher, the next thing is to draw conclusion from the analysis you've done based on your findings. Your findings determine the testing of your hypothesis. When your data comes out and you've analyzed, you look at your hypothesis, then your hypothesis can only be tested using inferential statistics. Going by this, if you use inferential statistics, that means you now have to tell us if your hypothesis, using inferential statistics, you have to tell us if your hypothesis was accepted, if your hypothesis was not accepted. No, or should I put it this way? If your hypothesis was rejected, that is, the hypothesis you raised was rejected. And if the hypothesis was not rejected, it means it was accepted. You tell us, okay, my hypothesis was not rejected, therefore my assumption was right. My hypothesis was rejected, therefore my assumption was wrong. The other thing is to compare your results with the previous experiment by other researchers. At the beginning, when you wanted to start your research, I said do literature review. You looked at the work of others, and I gave an example of those that if the work had been done in your locality or not. I talked about you want a clean and greener environment. What had others done? You looked at that work and probably want to replicate what that person did in your own locality, and peradventure the result differs. You look at what the person did that you did not do. Then you now look in what you look. Why should, if you did the same thing and your result differs, you now tell us what would have brought the differences, which will bring you to making suggestion for future studies. And if your result is similar, you also tell us, okay, my result, the findings was similar to the findings of so and so. At the same time, and this is why I think the findings were similar, you can also suggest that the work be done in another locality in order to give a general opinion. And if your findings differ, you can go over the research again and get things rolling again to get a result that would be beneficial to the human world. At the same time, drawing your conclusion, publishing your results ends the step in scientific research. I believe we've gained one or two things in this class today. I'll be waiting for your questions in the Telegram group. Be willing to answer them. If there are things probably in the previous class that you'd want us to dig deeper, you can drop in the comment section. God bless you.